Yeah, thank you for making it.
You bet.
Yeah, so we had a very interesting session today, and people are waiting for your session. Uh, just let me introduce Chris White. Quick introduction is we are talking about a topic stress testing of supply chains through digital twins. It's a unique topic, Mr. Chris White. Let me give a quick introduction. Mr. Chris White is a co-founder and CEO of SCM Blocks, United States. So Chris White, a seasoned expert in strategic, operational, and tactical issues, excels at phases of product and system development. His specialties include Six Sigma, Lean, organizational design, modeling, project management, strategic planning, risk management, and of course, supply chain management, and team facilitation, ensuring a quality and efficiency across diverse projects. So I have seen fantastic solution SCM Blocks from Chris, and I enjoyed it. I had a demo, and I wanted to introduce SCM Blocks to all the participants. So over to you, Mr. Chris. Good morning, and please, you can introduce yourself in a much better way, and then please proceed.
Oh, no, that was great. Thank you so much, Shaikh. And my apologies, everyone, for being late. I'm over in the U.S. and we goofed up on timing. So we'll get going here. So thank you. So let me share my screen, and we will get started. Let me make sure everybody can see.
Yeah, we can see it.
This screen, and now let me do that. And can everyone see this? Does this still work, Shaikh?
We are able to see the screen, but it is very small. Is it something?
Okay, so let me, we're going to have to do this a little differently then. Hang on just a second. It won't let me go into presentation mode. So can everybody, if I do, let me try this again. If I do it this way, let me make sure everyone can see well enough. Okay, I'll do it this way.
Yeah, maybe you can
And
put
is that big?
We can see it now.
Yeah.
You can put a slideshow.
It does not like it. Okay, it does not like it when I go into the presentation mode. So I'll keep it just like this and instead go through sort of slide by slide. So
no problem.
So thank you again. We're running a little bit late. We'll get this done though, and hopefully still have time for some questions at the end if anybody.
Your time and
if anybody wants. Okay.
Take your time.
Well, anyway, okay, take my time. Thank you so much. Well, thank you for the introduction. I think that was a good introduction. I've spent probably 30 years doing modeling and simulation, and probably about 25 years of that was applying that modeling and simulation to supply chain. So I've done this for quite a while. We do have a product, SCM Blocks, that does this. But what I want to talk to you about is just overall the idea of stress testing supply chains, because that is not necessarily done today. And stress testing, you'll see when we get into it, is kind of more of a long-term strategic view of the supply chain, which is missing today. And so we'll start there. The new reality, as we know, whoops, yeah, this is, give me just a sec, sorry about that. The new reality, as we know, is there's all these things happening. You got now, thanks to the pandemic and all these other disruptions, Panama Canal, Red Sea, you name it, there are all these huge impacts on supply chains now from a strategic standpoint. But the software and techniques we have are great at understanding what's happening today and tomorrow and next week, but they don't quite have the technology for looking long term in addressing some of these risks. So we need something like this. We need something. These are a couple of quotes from articles. Here's Harvard Business Review saying we need a stress test for critical supply chains. Supply chain movement stress testing uncovers supply chain vulnerabilities. Here's something from Forbes, and I've kind of highlighted down there. It's called New Rules, New Tools. But legacy supply chain tools just weren't designed for this level of insight. A new approach is needed. So we've been in the business of trying to incorporate this capability. And if you ever have any doubts, here's some real world examples. Here's Boeing that doubled the production of its wide body aircraft, did not prepare the supply chain for that, and ended up not getting parts. And so they had aircraft sitting on the production line waiting, and they had to write off $2.6 billion for that hiccup. Here's KFC, which not sure where they are necessarily globally, but this is in Europe, where KFC, Kentucky Fried Chicken, ran out of chicken. Quite interesting. $300 million impact. And here, this is an article by a news station in the U.S. where the chip shortage that we've been seeing over the last couple of years, has amounted to about $240 billion of financial impact. So these are not small impacts. These are big things that take time to sort of play out. And so we want to be in that business of understanding that. So we need to do something better. However, what we find, this is a study by the Supply Chain Risk Management Consortium, and they call it the strategic risk paradox. And it's very interesting. What you see on this chart is the blue bar on the right of each of these is the amount of time that we spend. So those blue bars add up to 100%. The red bars show the overall financial impact to the company. And they're on the left, and they're the red bars, and they add up to 100%. And what's interesting is we find that we spend 42% of our time on operational risks, the short-term tactical risks, but they create only 9% of the total financial impact. Conversely, we spend only 6% of our time. That blue line is way down at 6, but the red line is at 86%. The strategic risks and issues like the ones we just showed have an 86% impact on the total financial situation for a company, but yet we spend just a very, very small amount of time on that. So when we actually do something for strategy or long-term planning, we use a spreadsheet, and this is a report by McKinsey & Company. And so 73% of companies use a spreadsheet to do their long-term supply chain planning. So we use the simplest tool to try to help us understand and solve problems that are worth millions, if not billions of dollars, as we saw in those examples. So we're just left with this real simple tool, which isn't enough. We can't do that. We don't have the data, some people say. And so we're stuck with a spreadsheet trying to do that. We don't have the ability, we don't have the data to get into actually looking at supply chains like we want to long term. So I want to introduce something to you, because this is where the stress testing, the power of the stress testing comes from, is a different approach. And I want to pull this picture up, and this is just any process or system, let's just say. You've got inputs to that system, the activities that occur in that system or process or whatever, and then there are results of that system. So you've got input variables, all these actions and activities and operations that occur, and then results. I want to introduce two types of modeling to you. One is called statistical modeling, and that's what we use mostly today. If you've heard of regressions or correlations, those have to do AI, machine learning. They all use statistics. They care very much about the data. So what happens in statistical modeling is it attempts to look to the future by extrapolating or looking at the past data in their trends and patterns, things that we've seen in the past. So this approach ends up being very, very dependent on good, high-quality data, because the model itself is based on data. Now, it focuses on the results. So it focuses on data coming out of whatever process or system we're looking at. Notice it doesn't care about the process or system. It doesn't care what activities occur, what decisions we're making. It just simply says, I'm going to judge this system or process only by the data that comes out of it. So what's interesting is it does not do well to use this kind of model for forecasting if we don't have data that shows us what happens. So if we've never experienced it in the past, then it's impossible for us to create a good model for looking forward. And so that kind of embodies statistical forecasting, which is what we primarily do today. So what enables the stress testing of supply chains, like we're going to talk about, is what I call structural modeling. And now structural modeling instead looks at the activities. It actually doesn't care much about the results. Instead, it opens that black box of the activities and it says, I'm going to build a model that replicates and mimics these activities and decisions that we make. So the operations themselves. So we got statistical modeling that doesn't look at operations and only looks at data. And now we've got structural modeling, which is the opposite. It looks at the operations and doesn't look at the data. Now, I'm not going to say that data is not important, but when you're building a structural model, you actually don't need data at all. You just need the interrelationships and the interconnections among all the actions and decisions that happen, all those operations. Now, data is great and helps. If you have it, it's not required, but if you have it, then it helps you calibrate the model, make the model more meaningful, increases the realism of the model and all that. So what's interesting is because the structural modeling approach focuses on the cause and effect linkages and the operations, then it's actually a good way to look to the future because you can look at situations that you've never had before. Because as they make their way through the decisions and activities and operations, then the system adjusts and does what it would do. And so you can look at situations that you've never seen before. So when we start looking at long-term versus short-term, I want to kind of draw this out. And we've got time on the x-axis at the bottom and our results, whatever, some sort of data going up on the vertical axis. And so here are the past results, and they get us to this point in time. And now we're going to do a statistical forecast. Well, what's interesting is the system or process or whatever we're looking at, the momentum of that really doesn't change much in the short term. So the statistical forecast in the short term looks all right because the system itself really isn't going to make major deviations. What gets interesting is in the long term, where you really do finally see some big differences. And I've seen this in real life before, where projections go one way and the system goes the other, and we were able to predict the system going the other way. So decisions really, the long-term decisions, strategic decisions, are really only effective way out beyond the time horizon for which our forecast is valid and good. So all this happens beyond that. So we need a new approach for looking out there. And that's where the structural forecasting, the structural model, by capturing the operations and the processes and activities and decisions, it becomes the better way of looking long term to look at these situations. And it can capture these major changes in the system where you start to see the bullwhip effect and things like that, or I thought I was going up, but now I'm constrained and I go down. So it's very interesting. So let me just kind of summarize the pros and cons of each. And with statistical model, it is useful for the short term, mainly because the conditions really don't change much. So just about any forecast methodology is good in the short term. But by and large, we use that for the short term and it's good. And it's already built into a lot of our tools. So that's fantastic. The cons or the disadvantage is that sometimes it requires cleaning data, which can add bias, but we don't like that data point. It's a little too far out there, so we're going to remove that. So now it's not in the model anymore. And so that can kind of change the reality of that model. The statistical forecasting or modeling is also not effective for the long-term forecast. And like I said, especially when conditions are different in the future, because now our past data has no relevance to what's happening in the future. So all the data that we use to build the model are no longer valid. And also, since it treats all the activities, the system itself, as a black box, it doesn't include any of the actions or decision making, the adjustments that managers and executives make. Oh, we're high, we're going to adjust and go lower. All that is not included. It only looks at data. Structural modeling, on the other hand, is kind of the flip-flop. It incorporates all these operations and cause and effect or causal actions and decisions, And because it includes those management feedback loops of making adjustments, oh, we've got too much inventory, so let's not order as much the next time, or we don't have enough, let's order more. So it can actually show how things change as conditions change, and it can make the adjustments. And it is better for the long-term forecasting because it captures all that cause and effect. Now, the cons, the disadvantages of structural modeling is in the short term, it really doesn't offer anything different because, again, in the short term, just about any modeling methodology will work because the system has momentum and the data is really not going to change all that much in the short term. So structural modeling doesn't really add any value. And another disadvantage is that none of the tools out there right now, ERP or supply chain management tools, actually contain this methodology. So it would need to be added. And that's, of course, why we developed SCM blocks, is to be an add-on to these. So I want to go back with the initial title was stress testing through the use of a digital twin. And now I want to talk about what is a stress test and what a structural model can actually do. So I'm going to give an example here, or actually I'll say two examples, a comparison. And what we have on the left is a supply chain where I've got an OEM. I'm the OEM, the original equipment manufacturer. So I'm the manufacturer here, and I have three suppliers. So this is on the left. And I call this wide and shallow. So as the OEM, I'm getting three parts, and I'm getting them from three different suppliers, and I'll pull them together and put them into a final assembly. On the right, I'm going to look at a slightly different structure. Now I'm deep. I'm narrow and deep. So I have a tier 1. That tier 1 has a tier 2. That tier 2 has a tier 3. And again, it's three different things, but in this model, the tier 3 provides to the tier 2, who adds a little bit. The tier 2 then gives that to the tier 1, who adds a little bit. Then it comes to the OEM, who does the final finishing assembly. So roughly the same supply chain. Now what we're going to do is introduce a bump into the system. So what I'm going to do, I'm showing you this graph on the left, and what those variables are we can get into, but they're things like the blue line is raw material, so we're going to kind of focus there. All the other lines are production, deliveries, finished goods, but you'll notice that we start at the beginning in a relatively steady state, straight lines, and we finish in relatively steady state or straight lines. And of course, the real world is never truly steady state, but we can use that when we're talking about analyzing a system. We want it to be in steady state. We want to introduce a change. We want to see how the system responds to that change or perturbation. And then we want to see when it settles down or makes its final adjustments. How long does that take? So it's almost like, plucking the string on a guitar. Bing, we want to see how long that kind of takes. So that's what's happening here. And when we introduce this 20% bump, so you'll notice the blue lines at the beginning, and one's at 200. By that blue line for raw material, at the end, it's like 220. So 220 or 240, something like that. I guess if it's a 20%, then it'd be 240. So, but you see this rise with that. And again, this is the OEM. We're not looking at all the suppliers. This is the impact on the OEM. We see that our raw material oscillates a little bit. We kind of, because of that bump, we order a lot. Well, here it all comes, and then we sort of adjust. So the raw material grows by 35% above what it was, and it takes about 26 weeks or 6 months to settle down in this situation. Now, looking at the other supply chain structure that's narrow and deep, exact same bump of 20%. We start at 200, we end at 240. But you'll notice, even just looking at it, you can immediately see that the curves are different. And so on the right, with the narrow and deep structure, what we see is this a massive overshoot in raw material, where it goes up to 70% above where we were. So the wide and shallow on the left goes up 35%. This one on the right goes up 70%. But it settles down a lot faster. So it's chaotic, but it quickly settles down at this new level of equilibrium. So you've got two different situations here. Which one's better? I don't know. That's not what it's trying to say. It's saying that each system responds differently to the exact same change in that system. And we've got one that takes a long time but is a little bit more controlled. And we have one that's a little more chaotic, but it actually gets there faster. So it all depends on the situation of which one's better in this case. But the what I'm primarily showing is how we can stress test and see the results, and almost like a scientific experiment where we only change one variable. In this case, it's the structure. Everything else is the same. All the agent models for each of those boxes is exactly the same. So just that one change causes this to happen. Well, what about disruptions? So that was interesting. That was a change in demand. Well, what about disruptions? So I'm going to use that same model that we saw, the narrow and deep, where I've got an OEM with 3 tiers. And the black box at the bottom represents that the disruption occurs there. So now I'm going to do a scientific experiment where I'm using the exact same structure. And the only difference is I'm going to have the disruption occur for 2 months at the tier 3, then the tier 2, then the tier 1. So the graph that we're looking at is for the OEM, not the tier 3 that had the disruption. It's for the OEM. And so this looks a lot like the last chart that we saw for the OEM. There's a disruption. I lose a little bit, then I overshoot because I'm making more orders, and then I kind of finally settle down. What happens when it's at the tier 2? Well, we see a slightly different. Now remember, everything's the same except for where the disruption occurs. So now if it occurs at tier 2, I see some similar dynamics. I see a dip and then a rise and everything. But you'll notice that dip compared to the tier 3, because the scales on these charts are exactly the same. That dip goes further down, and my overshoot is even more, and then it takes me longer to settle down. So the tier 2 is a lot worse on me, the OEM. Well, and if we look at a tier 1, then what we see is a huge drop. Again, all the scales are the same, exact same model. The only difference is where the disruption occurs. So now when the disruption occurs at tier 1, I see this significant dip, and then I finally pull out. And in fact, if that disruption kept going at the tier 1, I might actually run out of material and not be able to satisfy my customer. So very interesting. So what we see is 3 different situations. And in fact, what it ends up being is the tier 3, if a disruption occurs at tier 3, because I have a tier 2 and a tier 1 in between me and the disruption, I'm actually not that impacted. Everyone else between me buffers that disruption because they are making their adjustments as well. So the worst disruption for me is close to me. So my tier 1 suppliers are the worst. And then it gets less and less severe as it gets further down in the supply chain. So very, very interesting when you think about that. Now, I want you to notice that no specific data were used in this model. So I didn't have to emphasize, oh, there's exactly 173 happening here, and I didn't reveal any information. I didn't have to have a bunch of data to do this. You could see that just even without data, we could tell the difference, a relative difference, in which one is, quote, better, simply based on these kinds of simulations. So what's great also, you'll notice that we're only changing one thing, one variable, like a scientific experiment, one variable at a time. The structure, where the disruption occurs, everything else stays the same. And because it's a computer model, you can just run, tens, hundreds, thousands of simulations for all these different situations. But what's key is the simulations will start in dynamic equilibrium, so, relatively steady state, so that any changes that we see between 2 different graphs is solely and completely due to the single change that we made and how all the different companies in the system are sort of reacting to that. So it's a very, very interesting. You don't need data, and you can kind of do this scientific approach. So I'm bringing up one of the graphs that I showed earlier, and I'm showing that the current methods that we use, we have network design, network optimization, and those are great where these arrows are pointing. In these steady state situations, they're great. They are good at being able to tell us what happens here and what we ought to do here. So they're only focused on this part right here. And so they are single point solutions. In situation A, here's what you need to do. In situation B, here's what you need to do. What they're missing, though, is this ability to look at this that happens in between, this dynamic change, the adjustments that everybody's making, everybody in the supply chain is making, and what happens in between these two steady state situations. What does it look like for me to go from A to B? Is it short? Is it long? Is it chaotic? I don't know. So that's where the stress testing and the structural model comes into play. Now, we talk a lot about supply chain resilience. And the thing with resilience is it's a system phenomenon. It is not one company is resilient. In a supply chain, it's the whole supply chain being resilient. So the only way to understand and assess resilience is to look at the supply chain and treat it as a system and stress that system through a digital twin. And that's what we're doing. And we want to see how that system reacts, how it recovers, how it responds to all these changes that occur. And so that's what we're doing with SCM blocks and the stress testing and using the digital twins for that. So I like to say that when we say supply chain management right now, it's a farce, it's a misnomer, it's bad usage of the word, because we don't actually manage supply chains. We manage pieces of the supply chain. We look at suppliers, our tier one suppliers, or we look at orders or inventory, but we rarely look at the entire supply chain from top to bottom to see what's happening in that whole system and how that whole system reacts, because I'm just one player in the system. There's all these other companies that are acting and reacting that I'm not accounting for. And even though I ordered 100 from my supplier, there's no guarantee. Even if I had a service level agreement that you must give me 100, there's no guarantee that I'll get 100 from my supplier if their supplier didn't give them 100. So there's a lot going on here, and you want to get into the rest of the chain. And this is where SCM blocks can actually stress test these deep supply chains, going deep, multiple tiers. I can look at if there's a fire that shuts this one facility down that's tier 4, or there's a hurricane in one area and I need to shift all my orders to another supplier. How long does that take to impact me? So with SCM blocks, we can stress test, I like to say, from top to bottom to top, because think of COVID, think of the bullwhip effect. Think of here in the United States, we had big issues with toilet paper and baby formula and personal protection equipment. We ran out and we saw these bullwhips that occurred. That's because the demand is so high, it clears out every tier of the supply chain. So the whole supply chain gets emptied from top to bottom. Then at the bottom, all the new products or materials are made, and it takes a while for that to go up the supply chain for the tier 4 to provide to tier 3 and get tier 3 back up, and for tier 3 to provide to tier 2 and get tier 2 back up. So it's really, we're looking at things that are major. We're not looking at small changes in demand. That's not interesting. Today's systems can handle that. We're looking at big changes. So we can do this, and as a digital twin, like I said, 10, 100,000 simulations to check every entity, every company in that supply chain for its vulnerability. What makes that company have trouble? Is it, if there was a disruption over here, did that cause trouble for this company over here? So we can look at disruptions anywhere in the supply chain, small disruptions, big disruptions. You just run more and more supply chains, and you can begin to kind of determine the weak areas of the supply chain and which areas are good at adapting, which ones are resilient, how long does it take to recover. You can just continue to pound this model, because it's a computer model, digital twin. Just run all these simulations, testing all sorts of variables and seeing the response of that system to those variables. So very interesting. These are a couple of things. We're commercializing SCM blocks right now, but this is where we developed SCM blocks, was for the United States Department of Defense. So the military in the United States, and these are real world examples of what we did. Now, gray boxes are kind of covering some of the things that we can't show, but what you see over here on the left, what we did for this helicopter program was understand, first of all, they didn't realize there was a choke point. So we see, if you see at the top, there's prime, and at the bottom, there's depot, and they each kind of have their chains that eventually come to this choke point. So they actually thought those two supply chains were independent. So the first thing was, whoops, you got a choke point. So let's figure out what happens there. That ended up not being too bad. So we also wanted to see if the system could survive certain, we'll call them shocks or whatever, changes in demand, changes in what the military was going to do. And what you see over here on the right, the top line, it's a green line. The top line kind of comes down and it never goes to zero. The red line, the line at the bottom, does go to zero. That's something else. But the green line is the one we care about. And what we were able to show them is that they did not have to go back and ask for more money from the Congress, which was on the order of $900 million. So we were able to avoid spending another $900 million because we showed them that under all the conditions that under all the situations that they thought they would experience, they would do fine with all the material that's already in their supply chain. So it's very interesting. Another one we did, again, I've grayed out anything that you can't see, but this was actually a much simpler model, but it ended up having a much bigger impact on the order of $1.2 billion, and this was an aircraft program. And I'm going to start with the graph that's on the right, the top graph, and you see a black line, but you see a bullwhip looking line. Now, where the black line and bullwhip line come together, I don't know if my cursor actually, if y'all can actually see my cursor, but right here, there's a red line, and you'll see there's a gap. And for this program, when you're trying to save lives, it's not about money. It's about having, the right system there for the military and saving lives. And they can't have this gap. So we started looking, and there were options for either adding capacity or moving inventory. And so their initial thought was, we're going to add capacity. So you see this in the middle chart, the black line goes up, and you'll see that it meets the top of the bullwhip. So they were able to handle that if that were to happen. But that costs a lot of money. And we came in and said, well, hang on, we've got this model, so let's start playing with other options in this model, because it's free. Just run lots of simulations. That's fine. Just let the model tell you. And we were able to show that if they moved some inventory around and created a little extra inventory in certain places in this supply chain, they did not need to add capacity. And you'll see in the bottom chart, that black line of capacity and the green line, the bullwhip effect, actually gets minimized, and they're able to survive with their current capacity. So they did not have to spend $1.2 billion to go add capacity to this one place in the supply chain. So it's very interesting. Another example, this was a missile program, and again, grayed out parts that you can't see. And I've just got a generic representation of part 1, part 2, part 3. And what we were able to show, now in this one, we didn't actually have a financial impact that we measured. Now we could go back and measure that, but that wasn't the purpose. The purpose was really to stress test this supply chain and check different levels of demand and make sure that everyone in the supply chain responded. So when it got to the OEM, the OEM stayed within certain bounds that they cared about, didn't go above this much and didn't go below this much. In terms of inventory, in terms of production. And so we were able to figure out kind of what the biggest disruption at different places in the supply chain, what that biggest disruption could be that would allow the OEM to still stay within its margin. So it wasn't quite financial, but it was, again, trying to understand how the system responds. And what we were able to do with this missile program is identify some key early warning indicators that as they watch these variables, then we have plans that say if that variable goes up, then do plan A. If that variable stays the same, then do plan B. And if that variable goes down, then do plan C. And so they have a playbook of all these responses, and they're just kind of watching the system to understand when to implement those responses. So again, those are real world examples of how you can stress test and use that. So SCM blocks can help understand what the vulnerabilities, understand and analyze vulnerabilities that you might have in your supply chain based on changes in demand. I'm switching from sole sourcing to multiple sourcing. What does that look like? How does that transition play out? We want to do it, but we don't know how long it's going to take. Is that 6 months? Is it 12 months? Am I going to suffer for a while that's happening? I don't know. So that's what we're doing. If there are long lead times, those often cause problems. If there are disruptions or delays, same things we've talked about. SCM blocks can also quantify or help you understand the resiliency of your system. How chaotic are the oscillations, the bullwhip effect? How chaotic will that be in your inventory and your production? How quickly can we recover and reach whatever new demand level or whatever new situation we're going to be in? And if we've got these big spikes from the bullwhip effect, what can we do to actually dampen those spikes a little bit so they're not as bad as could be? And last, just overall, by understanding all that, we can figure out ways to actually improve the performance of this supply chain system. Where can we move inventories that have the best impact or the best protection, the best impact? Can we alter our ordering patterns so instead of me doubling orders to my supplier, maybe I just increase by 25%, then another 25%, then another, and allow for the slow adjustment of my supply chain rather than hit it immediately with double the orders. So can I change my order patterns to minimize the volatility? Do I need to add or remove suppliers to kind of help me? You know, if I've got one supplier here and that supplier is in a country that maybe is having trouble, or at least for the United States, we have an embargo or some sort of trade dispute, and so that country's cut off for a while. So how long does it take for me to set up another supplier somewhere else and use that supplier instead? We talked in this last example, or the example with the aircraft. Do I need to add production capacity to be able to be ready for surges that might occur? So all of these things can be done with SCM blocks in some of the stress testing. So I'm going to kind of end there and leave that. And Shaikh, I'll turn it back over to you. I will stop. I don't see where I stopped sharing. Here it is. So I will stop sharing now and turn that back over. Did that work?
Deep,
Okay.
Yeah, it works. The presentation is now down. Yes, please go ahead.
Yeah, so I stopped sharing, so I took the presentation off so I can answer. If there are any questions, I'll be glad to answer some questions.
Yes, I'm sure. Shaikh must have a few questions.
So, Chris, very interesting. Actually it's a novel topic. Building digital twins for supply chain stress testing. It's not something very simple. Okay, there is a lot of knowledge behind this, and how can we do a specific industries like see, we do have like industries around automotive, food and beverages, and then these are like pharma, so very popular supply chains in India.
Yeah.
Okay, so how do you think we can adopt or we can try SCM blocks in this region, in these use cases? What is your advice?
Yeah. So what you saw obviously were military examples, but really SCM blocks doesn't care what the item is. SCM blocks becomes more powerful the more complicated that product is. So a car or some medical equipment or heavy equipment, if it's like say retail, I don't know if y'all have Walmarts over there, but big stores that sell a pair of jeans, that's not all that interesting for SCM blocks. But if you've got a refrigerator or like I said, a car or anything that's very complicated, then that means the supply chain is complicated too. And so if you just think of the bill of material, what makes up this thing, if it's a lot of stuff, then that's where SCM blocks works. And again, SCM blocks doesn't care what the product is, it cares how complicated it is.
Okay. I think it's a classic use case is automotive, especially, in India, we have a lot of challenges, especially for the tier one manufacturers. Okay. So there is a lot of uncertainty when it comes to tier one or maybe tier two suppliers. Okay.
Yeah.
So if somebody going out of business, then the whole OEM has a deeper problem.
Yeah.
Okay.
Well,
So that would be. Mhm.
I was going to
Yeah.
add what's interesting is SCM blocks can be used no matter where you are in the supply chain. So all these examples showed the OEM, but let's say I make seats for a car, seats with seat covers and mechanisms for, moving them forward and backwards and reclining and all that. So I make seats. I can use SCM blocks to look at my supply chain below me and not even worry about what's above me. The OEM may do a model that cares about me, but I'm only gonna in this case, I'm the OEM and I'm just looking below me. So SCM blocks can work at every level. Any company could use that within that supply chain to look at where they are and below them. So there's no
Yeah.
restriction to it just being at the OEM level.
Yeah, so it's as I understand from your presentation, it starts all the modeling from bill of material, and then
Yes.
from the bill of material, it's like a multi-level bill of material, and then
Mhm.
all the way you track to the vendors against each component, and then from there you bring back the risk. Okay, so
Right.
I think it's one of the best use case. What I think of is the pharma. Okay, so
Yeah,
you have a
pharma.
lot of ingredients where you bring it from imports from multiple locations, and
Oh yeah.
so many ingredients, so many components, so many parameters to watch for. It could be a
Right.
quality
And
problem.
like you
Mhm.
said, different countries that's another place where SCM blocks is powerful is anything that takes a long time. So within pharma, like that's nothing changes overnight in pharma. It takes
Mhm.
possibly years, it definitely months, if not years, for all these things to kind of come through. And so again, SCM blocks would be very powerful there.
If any partner does not, if any vendor does not renew his certificate or something, then whole supply chain has a problem in pharma.
Hmm.
Okay, so yeah, so what kind of data you need it? As I know from you that you don't have to have a lot of data to do the simulation.
Correct.
So what is the bare minimum data you need, Chris, to do
So,
the simulation?
so like we emphasize the bill of material. So as a starting point in any system, any supply chain, the bill of material often dictates and tells what the supply chain will look like. So if you have a bill of material that says I have this thing that's made up of two smaller things, made up of three smaller things, then you will have a supply chain most likely that has a big thing, has suppliers for two of the smaller things, has suppliers for the three smaller things. And so at a, without any information or without any data from who my suppliers are, I can just pretend and assume I have a supplier for everything that's in my bill of material. And let me just start with a supply chain that looks like my bill of material. And let me just start with kind of a default model that is a moderate model that says, they'll try to recover inventory and things like that. If anyone happens to know anything about the supply chain, then we add that information. So if someone says, "Oh, I know that that company provides these two parts," okay, great, we'll let them provide two parts. Or I know that company doesn't make to stock, they are make to order. You know, they don't keep a stock. They only make stuff when we order it. Okay, we can do that. So we add that in there, and that becomes the starting point. You don't need to know the capacities or anything. We just assume that everyone's at like 85% capacity, so they have a little extra room. But if you double orders, it's going to take them a while to do that. And then as you get data about the supply chain, you start adding that and you make it better. But you will get, even just taking that simple approach that I said and looking at the examples I showed, you will get about 2/3, 70% of your answer will just be from the structure, totally just from the structure. As you add data, you'll see that, you know, the oscillations that look like this maybe just kind of look like this. And so, but the behavior is going to be roughly the same. And all that the new data is going to do is get you a little better of an answer. So you might move from 70% answer to 80% or 90%, but you'll get most of your answer with no data, just looking at the bill of material. It's surprising. It's very interesting.
Fantastic. So how much time do you think, Chris, it will take for a mid-size organization to do a simulation and build a model?
Very good question. Not long at all. So if the company likes the models that are already in SCM blocks, then they can get started immediately, and, you know, within the first week have a model put together, their first model. It doesn't take, I mean, even in the first day or two, they could have that. If they look at the models and say, well, we do things kind of different, can you incorporate this? And so we would tailor the models, and we would need 1 or 2 weeks to do that, and then come train them and show them and all that. And so it might be 3 or 4 weeks, but within a month, you know, if you like what's already in SCM blocks, you're up and running immediately. If you don't like what's in there, then give us a couple of weeks to add what you want, and then you're off and running. So not long at all.
Fantastic. So I think it's a fantastic session. It's a very good idea to build a stress testing around the supply chain model. It's not easy because people don't think in that direction at all. Okay, in my experience, they all limit themselves to the internal supply chain, and then they are worried about only the vendors, and then they immediately
only their tier one
whole supply chain. Okay,
yeah.
So that's a practice, and eventually, if you want to really build a robust organization, and if you want to really make your supply chain a competitive advantage, I think doing a modeling for the supply chain blocks is very much recommendable. Yeah. So we look forward, Chris, from you. If any of our participants from this channel and then from YouTube channel, they are interested, we'll let you know for more insights and maybe a session required on this, because it's very important topic. In a given short time, I don't think it is possible to justify the complexity of that model. Okay, so I think you have done a great job of giving us a very nice explanation of modeling.
Thank you.
Okay, so thank you, joining, Chris, and we take this opportunity. Yeah, so I take this opportunity to thank all the participants and speakers today. So we are going to end the session now for today, and just to one coincidence is we had 10 speakers today from 10 different countries.
Oh,
imagine.
wow.
So I just took the list, and I find out that all 10 speakers are from 10 different countries. Okay, right from the United States. Yeah, the United States, from Canada, from Malaysia, from Singapore, Kuwait, Dubai, India, or whatnot. Okay, so I think we have the same scenario tomorrow, and I wish all participants to join with the same vigor and interest, and then let us learn from the best of the best speakers across the globe.